Welcome back to another riveting episode. Today we are going to go over this equation again. The reason I'm doing this is I want to sum it up into one nice video, because in order to figure out how I came up with this, you have to watch all my videos. So I thought I'd just sum it all up into one video, and to show you that it wasn't all induction to make this equation. There actually was a little bit of thought into it. So let's go over this again. So if you watched my series on the golden ratio to predict prime density, it ended up being a constant. And that's when the insight came to me that I can't have this be a constant. I need it to decrease as ln of x increases. And that's when I realized I have to put ln of x in the denominator of some sort of equation over here. And I thought of this as like a fine tuner in the corner to this number. And I tried many iterations of this. This is where the induction came from. Just tons of different kinds. And then eventually I plugged this in and it worked perfectly. I did not think E was going to work, but here we are. Now, I was shocked that it started at E and then tends to 1, because I thought E was just too high. But yeah, it just seemed to work. So here are some examples for you. Li of 10 to the 100, you get this answer. With my equation, this thing goes to this. As you can see, it's tending to 1, and then there's the number. It's different there, even those are pretty close. That's the difference. Ln minus 1 is a lot further away. And this goes for Li 10 to the 200. Here's your answer. As you can see, this is getting closer to 1. Here's the answer you get. It's pretty much similar all the way to there. And this one's different here. And then Li to the 10 to the 305. Yeah, as you can see, it's a lot better. And here it is. I changed E by 0.1 in both directions just to show you that this isn't a fluke of some sort. There's Li to the 200 again. You get this. There's my answer. Pretty much the same, 831,826. If we minus 0.1 from E, as you can see, it wildly goes under now, all the way to there. If you add 0.1, it goes over by a lot. So it is E. And here you go, here is Li to the 10 to the 300. It's 5,005 here at the end. Mine gives you 5,004. If you minus 1, you get 4,993. If you add 0.1, you get 5,015. Okay. So now, just to show that this tends to 1, it's kind of obvious. Ln of x will eventually go to infinity, which will make this 0, and anything to the 0 becomes 1. Now, once we've accepted this, we can actually write x over ln of x like this. All right. And if we set x equal to E, the equation looks like this. See? So if we square E, this becomes 2, and this becomes the square of E, the square root of E. We cube it, this becomes 3, this becomes the cube root of E. And this is where I got the idea that we are dealing with exponential growth and exponential decay, which to me invoked an unbounded infinity and a bounded infinity. So with an unbounded infinity, which is what we're used to using, we know where the integers are in relation to 0. Okay. Now a bounded infinity, we lose all the information of the integers, but we gain the information of ratios, of where things are. See, in an unbounded infinity, you can't find half infinity, but a bounded infinity you can. Okay. But in a unbounded infinity, you know where 2 is. You don't know where 2 is in a bounded. It's very uncertainty principle to me. Okay? They do give us 2 different kinds of information, but we can never combine them, right? You cannot put these together and then integers will appear here or ratios will appear here. That's how you deal with infinities. But we can mesh them together to get a better understanding of prime density. Now, another thing I came across, that the amount of primes between e raised to a power plus e raised to that power plus 1, okay, you get these numbers, and here's e to the 11 minus e to the 10, the amount of primes in there. And if you divide these, they tend to e. Okay, here's a big example to see it, right? The amount of primes between e to the 24 and e to the 25 divided by the amount of primes between e to 25 and e to 26 is that, and you can see it's tending to e. Now, a friend of mine did a bunch of great calculations for me to prove that this, as the limit goes to infinity, this actually does become 1 over e. So this is true. So how does this help predict prime density? Well, I want you to picture the primes growing this way, right? We got that information from what prime number theorem we have now, but this one goes the other way, right? So I want you to think we have e, and we're dividing it up this way. So here's the square root of e, here's the cube root of e, and it goes that way until it reaches its limit, which is right here, which is 1 to the e, which is that. So now we've combined the information of the integers and the information of the ratios going that way, which is this. So this idea, we're combining exponential growth with exponential decay. And here's another example of it. We take li to the e of this gargantuan number, multiply it by this one, and then take the one between squared. We get this huge number. Now, if we take this root of e, the same number, divided by this, we get a very, very similar number. I think they stop different here. So think about that. This one is about prime number distribution, all in an unbounded infinity. This one is about e to 1, exponential decay in the other direction, and they give us almost an exact number. Another thing we can point out is that Chebyshev gave us an upper bound and a lower bound for what this number can be, 1/2 and 3 over 2. And this particular equation does fall in between those two parameters. Now, to just drive my point home of how well this particular equation works, here's the equation up here, divided by li with this huge number. You can see tons of 9s. Here it is to a much bigger number. The 9 goes to there. Here's the same number with just using -1. The 9s go to here. So there you go. There's my equation all summed up for you. Side note that if you minus 2.5-ish here, it almost becomes exact. After about 10 to the 100, Desmos can't even tell the difference. I'm still trying to figure out why that's the case. Thank you for watching.